All right, let's keep talking about E2. Is there any questions from what we talked about on Wednesday? So what did we talk about on Wednesday in terms of E2? Now let's see. So what we said on Wednesday was that we have two bases that we can use, bless you, for doing E2, tertiary butoxide and NH2 minus. And the key that the reaction will be E2 is that these bases will be used. So when you see these bases, the first thing you think is E2. The tertiary butoxide is going to remove the less hindered beta hydrogen, whereas the NH2 will form, it'll form the most stable substituted product. So that's how we're going to determine our products. We're going to have to find our alpha carbon and our beta carbons and our beta hydrogens in order to be able to determine what products are possible. We also know that the base must deprotonate the hydrogen in an anti-periplanar transition state. And that's what we're going to focus on today, is applying that anti-periplanar transition state to cyclic and acyclic systems. Okay, so that's what we're going to start with. Okay, so that's where we're at with E2 reactions. Now, let's talk a little bit about this idea of putting the hydrogens in the anti-periplanar geometry, because you'll see these problems in the book. We have acyclic systems and we have rings. So one of the things that we could think about is this. We have a molecule that's in a sawhorse projection. And let's say we have our chloride here. We'll put a methyl group there. We'll put a hydrogen there. Let's put a hydrogen here, put a methyl group here, and put an ethyl group there. So if I gave you this molecule and I said, let's write all of the products for E2, and for the sake of argument, I'm going to go ahead and I'm going to use NH2 minus here. What we have to do first is we have to identify all of our beta carbons and beta hydrogens. So that means that we need to identify the alpha carbon first. Then here's a beta carbon, and then here's the other beta carbon. And so the beta hydrogens then are, if I wanted to change this from a CH3 to a CH2 with an H, there's one beta hydrogen and there's two beta hydrogens. So there are our two beta hydrogens, and we'll call this beta hydrogen A, and we'll call this beta hydrogen B. Now, I guess the one thing I have to point out, but you have to listen because this is not a hydrogen that's going to be deprotonated. You might say, what about this hydrogen over here? That's an alpha hydrogen because it's attached to the alpha carbon. So nothing happens to it. Okay? We're only looking at the beta carbons, and then the hydrogen is attached to those. So we have two possible hydrogens that can be removed in this process. Okay. And if I wrote the structures of these two products, let's say for product B, I would say, okay, nothing's going to happen to the left chiral carbon. And that's what it is. The way I've written it, I've set it up so that it is chiral. What would happen is the base would come in, it would grab the H, the pair of electrons would move here, and the chlorine would get kicked off, so that I would have a CH2 double bond and then the alpha hydrogen. So this would be product A. Okay, so nothing happened at the chiral center on the left. Only the CH2. Now my question is, if this is NH2 minus, is this the major product? If I'm doing this reaction with NH2 minus, is A the major product? Yes or no? All right, let's vote. So, is A the major product? We'll make it A yes, B no. Okay, has everybody voted that can? All right, we've got 25 B's as no. Why not? Why isn't this the major product?
Because it would, the NH2 forms the most stable substituted product.
And that's not this one. That's not this one. So this is not the major product of the reaction. But it is still a possible product. And as a matter of fact, if I wanted to form this product, what base would I use? If I wanted this to be the major product, what base should I use? I should use the other base that we've talked about, which is tertiary butoxide. Okay, so what is the major product of this reaction? Well, that means I'm going to remove hydrogen A, beta hydrogen A. But beta hydrogen A is not anti-periplanar to the leaving group. So I have to make it anti-periplanar to the leaving group. And so how am I going to do that? Well, I'm going to have to rotate hydrogen A so that it's it's anti-periplanar to chlorine, and then I'm going to have to move the ethyl group where the methyl group is and bring the methyl group to where the hydrogen is. So I'm going to have to rotate around this sawhorse projection. And so when I do that, I'm going to end up with the hydrogen here. Now over here, nothing's changing on the right chiral center. But I'm going to have to rotate the hydrogen there. Then the ethyl group will move to the dashed position, and the methyl group will move to the bold position. And if you didn't like doing that in the sawhorse, that's the most direct. But if I was to draw out my Fisher projection of the original molecule, or Newman projection looking down that bond, I would have the ethyl group on top. I'd have the chlorine in the back down. The CH3 here. Nope. CH3 is attached to the back carbon. That's correct. Yep. Then I would have the hydrogen on the back, and pointing towards me is the hydrogen, and pointing away from me is the methyl group. So this would be the Newman projection looking at the original molecule. The hydrogen, I'm looking to put this hydrogen anti to the chlorine. And so that's where I would have to rotate the hydrogen up to where the ethyl group is, down here, and then the methyl group going there. So the geometry in which the deprotonation would have to take place is to have the hydrogen, then the ethyl group is over here, and then the CH3 group is there. So this would be the proper Newman projection. This Newman projection corresponds to looking at the molecule from the left, looking down that carbon-carbon bond. Either way you put the molecule, it has to be placed in that conformation, because that's the anti-periplanar conformation for the hydrogen. So now when the base comes in, when the NH2 minus comes in, it kicks off, it takes the hydrogen, forms the double bond, kicks off the chlorine. But now the geometry around the double bond is fixed. And down here what will happen is the base will come in, it'll grab that hydrogen, that pair of electrons will move to form the double bond, the chlorine gets kicked off, and so the groups that are on the same side will end up being cis, and then the groups that are on opposite sides will be trans. So up here, the final product would have a CC double bond. The groups that are on the two bold wedges will end up cis. So that means the methyl group on the left side and the methyl group on the right side will be cis. And then the ethyl group and the hydrogen, both on the dashed wedges, will also be cis on the other side. So this is the only alkene that's formed in that reaction. The one where the two methyl groups are trans is not formed. And then if you looked at it on the Newman projection, the Newman projection is kind of strange because it would have a methyl group on this side, it would have the ethyl group on this side, and then on the back it would have a methyl group and the hydrogen. So what happens is these groups just basically come together and flatten out. And that's what makes them cis. Okay. Does everybody kind of see that? I mean, we're going to have to test this in a minute. So if the beta hydrogen is not anti-periplanar, you have to rotate it to make it anti-periplanar. And then when you do the elimination, you'll get the double bond with the two bold things cis and the two trans groups cis. You will not get the other product. Kind of okay with it until we have to do one. All right, let's do one then. And I can vary these, so we'll start with something. Let's start with something that's similar to what we just did, and then I'll crank up the intensity on this. So the H there, let's put a CH3 group here, let's put an ethyl group here, let's put an ethyl group here, and let's put a hydrogen there. And let's do this reaction with NH2 minus. Okay. And again, alpha carbon, beta hydrogen 1, beta hydrogen 2. So beta hydrogen A, bless you, beta hydrogen B. So what I would like to know is, in the alkene product that's formed by NH2 removing beta hydrogen A, what?
I thought that hydrogen would be alpha hydrogen.
You are correct. See, good catch. That is not a hydrogen we're going to remove. Just illustrating a mistake that you could potentially make unintentionally. But it still works the same way. This is our beta hydrogen on the CH2. Yes. Okay. So if I'm using tertiary butoxide, beta hydrogen B is going to be the one that is deprotonated. But now I want to use NH2 minus. So I'd like to remove beta hydrogen A. And so my question is, when you remove beta hydrogen A, which of these two products do you form? Do you form product A or do you form product B? All right, so I will go ahead and make that a multiple choice question. Good, I don't see anybody immediately answering, because if you're immediately answering, then you can see this thing in your head better than I can, which good for you. But this is going to take some drawing. Okay, so I'll give you like 3 minutes or so. Going once. Okay, everybody's answered. And we have a split. So you know what we do now. Discuss with a neighbor, and then we will revote after you've discussed with your neighbor. So I'll give you a minute for you to look at the other person's work and see if they got it in the right place. Okay, let's go ahead and revote. Let's see if we move towards an answer. Okay. Going once. Twice. 3. We didn't go anywhere. We're still split. All right. Okay. That's fine. So, tell me, what do I need to do? I need to move the hydrogen on the left to that position, right? Well, then what goes on the other two positions? And that's essentially what we're split on. So if I bring the hydrogen from the back to the methyl to the bold, and then the CH2, or the ethyl group, to the back position, where does the methyl group go? It's going to go to the bold position, right? So if I rotate this, I'm rotating this, and if you need to, we could write out the Newman projection. So the Newman projection of the starting one is the CH3 is here, the ethyl group is here, the hydrogen is here, and then the bromine is down here, along with its hydrogen being back, and the ethyl group being on the bold. So if I rotate this hydrogen up here, the methyl group's going to come forward, the ethyl group's going to go to the back. So I'm going to have my hydrogen here, my ethyl group, my methyl group to the right, and then my ethyl group over here to the left. So now when I do my deprotonation, the ethyl and the methyl group they're on the same side, which means the methyl group went here and the ethyl group came to the back. Now do your deprotonation and you end up with the C double bond C, where the methyl group and the ethyl group are on the same side, and the hydrogen and the ethyl group are also on the same side. So that's product B. Yes, no. So I guess whichever way works for you. If you can see it in the sawhorse, great. If you can't see it in the sawhorse, then you're going to have to put it into the Newman projection.
How did we know we had seen the hydrogen?
Because this is the beta hydrogen and it has to go anti-periplanar to the bromine. Right? It has to go into that anti-periplanar geometry. And this is the geometry that you will always need for any acyclic system. For a non-ring system, you're going to have to put it in this sawhorse, in this staggered conformation. Okay, does that? And I have some problem sets that we could do in class, but I know that in the book they have a lot of problems where they're asking you to do this exact thing. Of course, you get two answers, so I guess if you get the first one wrong, then reverse it and you'll get it right the second time. But that's not what the homework problem's about, right? The homework problem's about if you don't get it right, okay, now what did I do wrong? And then hopefully the next one you'll be able to do it correctly. So does that kind of make sense? So any sawhorse that you're given, you've got to put in this conformation, you've got to put it into the Newman projection where the leaving group is here and the hydrogen is there. That's the conformation that you have to put it into. And then these groups will be cis and these groups will be cis. Okay. All right, so does that make sense? Because what I'll do is I'll leave some of the problems in the book for you to do. If I get a chance over the weekend, maybe we'll start with a, what is it called? A bell ringer. When we come into class, I'll give you a couple of these problems and you can go ahead and answer them and we'll see how we've progressed. But the next problem I'm going to give you is going to look like this. Right, I'm going to make the sawhorse a little bit different. And I forget, is this sawhorse, is that eclipsed or staggered? It's eclipsed because all the bonds are in the same direction, so they're eclipsing each other. So for this one, you might have to put it in the Newman and then take this, make this position all the way up here, so that's where your hydrogen can go. But we'll save that for Monday. What I want to talk about is something that's actually a little bit easier to see, and that's rings. Because I want to do both of these cases. So what happens in a ring? Well, rings are really easy. Because if I use a flat cyclohexane ring, and I say, oh, here's my leaving group, and then I put let's say I put a methyl group here, with my hydrogen there, and then down here I put an ethyl group there with my hydrogen there. We would say, bless you, alpha carbon, beta carbon, beta carbon, beta hydrogen, beta hydrogen. So I've got hydrogen A and I've got hydrogen B. So in the flat cyclohexane ring, which hydrogen do you think is going to be removed? And we'll just go ahead and we'll use an NH2 minus. Which hydrogen do you think will be removed by the NH2 minus? Do you think it'll be beta hydrogen A, or do you think it'll be beta hydrogen B? And it can only be one. All right, nobody wants to give me a public answer, but I do have the wheel of misfortune up. But why don't we just do this? Which one do you think is going to be removed, A or B? I'll give you a minute to discuss, if you'd like to discuss. So which one do you think is going to be removed, A or B? And I'm asking just to see what your kind of gut feeling is as you look at this. I'll tell you in a minute and why, but I just want your initial gut feeling here. So if you're like, I don't know, okay? Think about what would you need to know? Everybody got an answer? Don't want to change? Okay. Let's see what you guys think. Kind of a split. Okay, that's okay. So here's the issue. Well, no, let me ask. Somebody who said A. Why'd you say A? Melanie? Okay, so you want them to be they still have to be anti in the chair conformation, which is going to correspond to. So if I put my chlorine, well, my chlorine is up in this case. So where down here, where would if I have to have a hydrogen, well, I'll just do it this way. Here's my hydrogen E for equatorial. Here's my hydrogen A for axial. Which hydrogen is going to be removed, or which hydrogen will be removed? The axial one or the equatorial one? What's my restriction again for E2? The hydrogen has to be anti-periplanar. So which one of those two hydrogens is anti-periplanar, HE or HA? HA? Do we all see that? No? Okay. Let's look down this bond and let's put it in a Newman projection. I don't know whether that's going to help or not. But if I look down this Newman projection, my front carbon is oriented like this. It's got bond, bond, bond down. My back carbon up here is oriented like this. Down, down, up. Where's my chlorine? On an axial up position. Down here, here's my HA, and here is my HE. And then over here, what's this? That's the rest of the ring. If you don't like that, you saw these kinds of things in the book. That's the Newman projection if you looked at the cyclohexane ring. But I'm only interested in this part. So the HA now is what? Anti to the chlorine. So HA is the only one that can be removed. Do you see that? I'm not getting a lot of feedback here. I'm getting a lot of just blank. I want this to end. It's way too early for this to end. We still have like a month. Right? So if you're done with organic, this is not the time to be done with organic. December, second week, you can be done with it for a while, but too early. Okay? Does that make sense? These two positions are anti. Now, if you're worried, if you're saying, well, but I thought before we said that we wanted the big groups to be equatorial. Yes, we do. But if we're going to undergo an E2 reaction, we have to add energy to the system in order to make the ring flip and put the leaving group in the axial position. So I'm not talking about stability here. I'm just talking about making the molecule undergo E2, which means that the leaving group has to go in an axial position. Okay. So then the hydrogen that's anti to that is going to be what to the leaving group? So here's my leaving group. Here's this hydrogen. What relationship do they have? Cis or trans? Right. On 3. 1, 2. They're trans, right? Above or below the plane? Above. Above or below the plane? Below. They are trans. Okay. So, whenever you're doing a ring, in order for the molecule to form that antiperiplanar geometry, the leaving group and the hydrogen that's going to be removed have to be trans. They have to go into the axial positions, and since they automatically have to be 1, 2, because that's what alpha and beta is 1, 2. When you have the groups 1, 2 to each other, then that means that the other group has to be axial in the opposite direction. That's the only way they will be anti-periplanar. So it's actually a little bit easier to look at the flat cyclohexane, because in the flat cyclohexane, that means that the beta hydrogen has to be trans to the leaving group. So HA is what? Is it trans or cis to the chlorine? It's trans because the hydrogen's on a dash and the chlorine's on a bold. But down here, HB is what to chlorine? Cis. Because they're both bold. So this hydrogen cannot be removed in an E2 mechanism. Ever. The tertiary butoxide can't remove it. The NH2 minus can't remove it. This one cannot be removed by E2 because it's cis to the leaving group. The only one that can be removed by E2 is the hydrogen, the beta hydrogen that's trans. Okay? So the reasoning is because of the chair cyclohexane and the fact that the group has to be in the axial positions. But once we see that, we can forget about that idea and just say, okay, when I'm looking at a flat cyclohexane, the beta hydrogen must be trans to the leaving group to be removed in an E2 mechanism. Now, in an E1 mechanism, which one can be removed? In other words, if the chlorine leaves and I form a carbocation, which hydrogen could be lost? HA? Could HA be lost? Yes. Could HB be lost? Yes. Because once I form the carbocation, it doesn't matter whether it's parallel up or parallel down, because the carbocation has the empty lobes. So in E1 mechanism, both of those hydrogens would be lost, would be potentially lost. And then what would the major product be? If it was E1, they both could be lost. The major product would be the one that is most substituted. And actually, in this case, it would be both. They both would be the major product. Because it doesn't matter whether there's an ethyl or a methyl group, because our thing is we're counting groups regardless of what they are. Okay. Right. So, from this problem, I can ask you 3 different problems using this cyclohexane. I could say, what was the major product with NH2 minus? I could say, what's the major product with tertiary butoxide? And I could also say, what's the major product if it goes E1? And I will do that. Okay. And the book will do that probably as well. So that's how we handle cyclohexanes. It doesn't require as much rotation as the acyclic ones, but we still have to understand that E2 must go anti-periplanar. There's no other way. So, what we'll do on Monday is, because we'll wrap, because I think the next chapter in the book is kind of wrapping up E1, E2, SN1, SN2, which I think we've done a lot of. But what we need to do is we need to do some of these problems. And so my recollection is that I have a sheet of these problems. We'll start with some at the beginning of class, so I'll put some on the board, and then you can come in and you can talk and you can put your answers on the board. We'll go over that, and then we'll do some problems either in groups, or we can just choose some problems and have you do them. And so we will dedicate Monday to a problem test or problem things. All right, your exams, I'll post the answer keys. The answer key to this when I get back to the office. I will be diligently spending the weekend upgrading the grade book because I know I'm behind. I'm behind on so many things right now, it's not even funny. I will hopefully have the grade book all up and together on Monday. If you have any questions about this, if I made a mistake in points or anything like that, bring it to me. That's possible. All right. So on Monday we'll have more of an idea of where everybody stands in there, where they're at. And the curve on this, instead of 142 points, it'll be like 135. So